And welcome back to a kind of teardown. It's apart from my Discovery. That's called a body control unit. And the Discovery is full of water because it leaks like a sieve. And I think this is causing problems. So let's take a look inside. Now we can get in just by pulling down on the tab and pull the screwdriver. There we go, on there. And we're in. And it's out. As has been sat on a radiator for a day. Let's have a quick look at what we've got. There are 5 plugs. 1, 2, 3, 4, 5. So if you turn it up, you see there are 5 sections. And one of the other problems with my car is the horn. When the car gets damp, you press the horn and it stays on and blows the horns. So when I got it, both the high and low tone horns were broken and they wouldn't work at all. Then after the summer had been on it for a while, they did. And I put another horn on, and I noticed the other day that I bibbed the horn for some reason and it stayed on. I had to turn the engine off, wait a little bit, turn it back on, and then it was okay. So I promptly took the fuse out. So this is the board in all its glory. Right, we'll have a look at some of the components. There are quite a few that are the same. You know, you might notice that the circuitry around there, and that one all look the same, and that's because it's the same component. They're all doing a similar job. So let's bring the microscope on and we can have a look at what the first components are. We have a BTS 141, and what I'll do is I'll show you the component and then we'll jump to have a quick look at the data sheet. Right, hopefully we can all see this. This is the BTS 141 and logic level input. So that's probably a 5 volt logic level input. VDS maximum 60 volts, 28 milliohms on, and it can carry 28 amps, but nominally 12. So designed to carry resistive, inductive and capacitive loads and suitable for 12 or 24 volt applications. And it's intelligent. It has some speed limiting by the look of it. It has some current limitations, over temperature protection, short circuit protection, overload protection, and some ESD protection. So reasonably good FET. So yeah, if you want to find out more, it's on Infineon, and just go and look it up. So we'll look to see what the effectively the VDS transition voltage is. And yeah, V and TH maximum 2.2 volts. So you could drive it from a 3.3 volt output if you want. But say, if you want to look at more of the data sheets, you'll just have to go and look them up. I won't be providing links. So moving on down, we have a BSP 62 and another one, and there's another one there. It won't really focus on it. Will it focus? Can't really make out the oh, there you go, BSP 62 got the light on it. Right, we'll just breeze over this one quickly. Yeah, BSP 62 is a 2 transistors, that's a Darlington as it said. BSP 62, maximum voltage between the collector and the base, minus 90 volts. Collector and emitter, minus 80 volts. Up to 100 milliamps of base current. Characteristics, HFE, minimum 150 milliamps, minimum gain of 1000. go up to half an amp and you've got a gain of 2000. And the saturation voltage, this is the important bit. Collector emitter saturation voltage, 1.3 volts. Now that gives you a hint of that when this is fully on, the voltage across there. So if you were using this to drive something that wants to see I'll say a logic low of less than 0.8 volt, you're not going to get it. That's quite an important one, BCE saturation. The maximum voltage you might see across the collector and emitter, and that has to be lower than your minimum low level signal that you want to see. Doesn't matter about minimum and typical, but the maximum has to be lower or you run the risk of it not working. Right, on to the next one. And we move over here and we have a VND 3N. Right, here we can see the VND 3N. It's a reasonably good looking MOSFET. And we can see here that RDS 120 milliohms, 3.5 amps. So let's have a quick look down. Block diagram. As you can see, it has over temperature protection, it has linear current protection, it has an old over voltage clamp, and it has the gate control. So it's quite a clever little device. And we'll move on down just to some of the ratings. And here you can see its ratings is -40 to +150. So good for being in a car sitting outside in the cold in most parts of the country. Input threshold voltage, which is will it work with your logic chip? Well, if your chip can produce more than 2.5 volts, then you'll be able to turn it on nicely. So it's pretty good. Drain current limit to 7 amps max. Over temperature shutdown, 175 degrees C. You can get it up. I'm sure by then it would have probably fallen off the board. Anyway, all these data sheets are available on the web if you search for them. And so I won't go much further into this one. There are a couple of these, well, there's 3 of these chips. Oops. Which, as you can see, are a ULQ 2004. There is, so the one we're looking at, one over here, and one down there. A ULQ 2004. Right, here we have the circuit. So you can see exactly how it goes together. And this is the package outline. So here we have the common freewheeling diodes, which is handy because if you're driving an inductor, you know, you can use this and it will clamp the back EMF. And then we can go down to look at some of the various things. Different currents for the saturation voltage. So if you're pulling 350 milliamps, you can expect to see a maximum of 1.6 volts. So again, you've got to be careful on how low you need to pull the output to see if a chip like this is suitable. And forward gain of 1000, because it's a Darlington, it's going to be high. So there's plenty of other things you can look at. But as I say, before you use these chips, I recommend you pull down the data sheet and have a look at them. So we got about 6 CD4051s, which are analog multiplexers. Here we can see the CD4051, and as you can see down here, it's a common in or out, and it can be switched between channel 0 and channel 7. So there's 8 inputs or outputs. I think the 4051 is bidirectional, and then we have three bits for controlling it. And if you look at the difference between the 5.1, 5.2 and 5.3, is the 5.1 has 1 channel, the 5.2 has 2 channels, and the 5.3 has 3 channels. So the last digit designates how many channels you have. You can pause and read the descriptions and the features. But as I say, it's best to download. We have the main, well, we have some transistors, which is a Y12. Right, so we can see here we have a BZX84 series Zener diode, and it's in a slot 23 package. And if we go down, we will see that one on the board is marked Y12, which makes it a 33 volt Zener. Now, they tend to put Zeners on the input signals into devices on cars if they're coming from outside your unit, but because of what's called load shedding. And when your alternator is pumping energy into, say, a fan, big fan, radiator fan, and then the temperature is deemed to be okay, and the fan stops, the alternator cannot react to that relay clicking out fast enough. And so before its control mechanism catches up and brings the alternator back under control for the load it's now got, the load disappears, so the voltage shoots up. And that's under a term called load shedding. And so they're protecting the input of the devices to less than 33 volts or less than 35 volts. And so as long as your device can withstand that, then you're protected. There's a 5BS. Right, a 5BS is a BC807 variant. We'll go down and we'll see the various package outlines, and we'll come down here and you can see package marked 5B is a BC807-25. So it's a 45 volt half an amp PNP general purpose transistor. Another 5BS, and somewhere around there is another version. If I can get it to highlight some of them Y126. Some of them don't really show up, they've got some gunge on them. But there's a 6BP. And here we have the 6B, which is an NPN 500 milliamp 45 volt. The sort of the complementary component of the 807. So we come down and it's a slot 23 device. And here we have 6B BC807-25. So that's a complementary transistor of the last one. We have a TPIC6A595. TPIC6A595 is quite an interesting chip when you look at it. It is, according to the spec, a monolithic high voltage, high current, power logic 8-bit shift register designed for use in systems that require relatively high load power. The device contains a built-in voltage clamp on the outputs for inductive transients protection. It's designed for driving things like relays and solenoid and other medium or high current loads. So when we look at it, here we can see there's a bar G, which means it's active low. And when it's low, all the outputs are turned off, so they float up. There is a serial in to the 8 flip-flops and a serial out. There is a SR clock to clock the data through the flip-flops and out if you want to cascade them. Once you've clocked the 8 bits through, you pulse the register clock, and that transfers the data from the flip-flop side into a second bank of flip-flops which drive the output. We'll come and have a look at this, and as you can see, there's the G, and it just controls all the outputs. And so if it's low, these are all off. And then we have a serial in, which, as you can see, cascades down all the flip-flops. There's the SR clock, which goes into all of the flip-flops. And so basically you clock in your data pattern into here, and then once you've got the required data in, you take the RCK line high, then low again, and that will latch that data into here. And as long as G is high, the respective drain or FETs will be turned on and the drains will be pulled low. And there is, if we come down a bit further, right, we'll just look at the timing diagram, and time is flowing from left to right. So the first data to be clocked in is for register 7. So on the first pulse, which is the bit 7 on the rising edge, our input data is low. On the rising edge of the pulse afterwards, the second pulse from flip-flop 6, it's high. For the third pulse for flip-flop 5, it is high, and for flip-flop 4, it is low. Flip-flop 3, it is low. Flip-flop 2, we have a high. Flip-flop 1, we have a fly high, and flip-flop 0, we have a low. So at the end of the 8 pulses, we want to get that data in. So the R clock, register clock, goes high and then low. On the rising edge of it going high, that data is flipped in, and then a period of time later, the outputs change. And that is obviously the delay of it going through the system. And as you can see, 1, 2, 5 and 6 have gone active low, and we look up here, 1, 2, 5 and 6. When going low to high, they were high, and the same for drains 0, 3, 4 and 7. When the clock was on the rising edge of their associated clock pulse, they were in the data, input data was in the low state. So quite simple. And if you keep G if you keep G low, then the outputs won't change while you're clocking the data in. They will only change on the rising edge of the register clock. Moving over, not sure what this one is yet. It's an 04DT3TK. Quick look at this one. We have a LP2901, which are low powered quad differential comparators, and got the sort of strange configuration of, ins at the bottom and the outs at the top. Quite often you can see them where you have like in, out, and in, out, and out, in. So it's a different way of viewing it. One of the other differences between a comparator and an op-amp is if you come down to the circuit into the schematic diagram inside, you'll see that the out has no pull-up. Op-amps can pull down as well as pull up, whereas a lot of comparators are open collector or open drain, meaning that this can only pull something down. You need to feed current into it in order for it to pull that current to ground. So you need an output pull-up resistor. Back to the board. Over here, a TLE 4269. Well, the TLE 4269 is an interesting choice, as it's a 5-volt load dropout fixed voltage regulator, and it is linear. So it's unusual nowadays to have a linear regulator due to the heat involved if you're pulling too much power. But looking at this, it only has a low output current. It's only about 150 milliamps. But I think what they could also be using it for is it has a reset function, which is if you're running a microprocessor and you want an external reset that's better than the kind of reset function that the microcontroller has, then one of these is an ideal solution, because not only does it give you the nice 5-volt supply to your microcontroller, but you can delay the reset once the reset has gone above a certain voltage. So it has a delay feature built in, so you can have, and you can adjust the reset threshold slightly. So that very good in automotive applications or noisy power supply applications when you want a decent reset. Far better than using the reset circuitry that's built into your microcontroller. And here's the block diagram. I won't go into much more detail with this, apart from I expect the reset output of this is probably going to the reset of the microcontroller, and the one on the board is the 14-pin version. And I have buzzed around, and all the pins that are going to ground go to ground. So it definitely is the right chip. I just haven't gone as far as seeing where the reset output goes. But I would hope, because they've got this chip, it is going to the microcontroller. So back to the board. There is a little one down here, a 7555. I think that's a Philips symbol, which is a CMOS 555. As you can see here, 7555 is a general purpose CMOS timer, and it is, slightly improvement over the 555 timer with exactly the same pins, threshold, trigger, reset. So it's just a modern version. It was a modern version back in about the 70s. So, and I think it has exactly the same pinouts, threshold, control voltage, trigger, discharge and output. So I won't go into much more about it than that. Anything else of interest we have? Another VND3N, an ND14NVO, and the main chip, which is a BCU 08-01, that's lasered in, but the main part is a Motorola part, which, if we come back a bit, is an XC528647CFN4, and I can't find any real data on that because it looks like to be a custom specific part, obviously, because it's been programmed, and that top part is lasered in. It's not printed. It's a laser etch. And then there's, noticeably over here, move that out a bit. Couple of relays and some big these are obviously current shunts, 33 milliohms, and there's 2 of them, so it's obviously measuring the current going somewhere. And one of the issues I've got is on pin 4 of one of these connectors. I can show you the data sheet, but pin 4 on one of these goes to that chip. You've seen the data sheet for that by now, and that will show you that it's effectively going to the end pin down there. And at some point I'm going to lift that last pin on this side. I'm going to lift it up just in case that chip is faulty, because that will stop my problem with the horns bidding. So hopefully we've seen enough of that. So let's just turn that one off, bring it out of the way, bring that back mainly into shot. So there's nothing on the other side. I'm not going to try and debug the circuit because there's quite a lot of tracking and quite a lot of the components. 2 megahertz crystal for the main controller and some capacitors. Now I'm going to put this back in the car because I want to see if it will run so I can use it. But the 5 capacitors I'm going to hopefully change out in the new year. I'll take it back out again. It doesn't take long to get out. I'll take it out and put some new capacitors. So I'll recap it. And then I'm in 2 minds whether to conformal coat the board. And if the horn fault goes away, I shall leave that leg sat up in the air. If the horn fault doesn't go away, then when I recap it, I'll put the leg back where it belongs. So if you like what you see in this video, click on the like, hit the notification button and click on subscribe if you want to see more of it. And I'll catch you in the next one. Well, just as a little snippet at the end, here is a quick video speed up of me playing at lifting the last leg. So a bit of fresh shoulder. Oh, I got a terrible cough today. Bit of fresh shoulder, and then it's just gently getting a scalpel blade underneath until you can pass it all the way underneath, and then gently lifting it above, and that will probably be good enough. It's far enough away from the board not to make a connection, and I'll just leave it in here like that, put it back in the car. Thanks for watching. Catch you on the next one.